All right, I think we're ready to get started. Today we've got a couple of things that we have been working on with our Thermistor SD card. We're going to use the SD card today. I brought out a micrometer so that we can look at how it works. A little bit of linear regression, and maybe some coding in Python a little bit. Not a whole lot, but just a little. We actually will do a little bit of Arduino coding today too to get our SD card working. Let's start with the micrometer. So another measuring tool, similar, to a caliper in that there's a gap between two measurement points, and you're measuring that gap basically. The differences are, so technically this micrometer can measure down, it has markings to measure down to 10,000ths of an inch. Although on it, it shows you that, let's get zoomed in a little bit. There we go. It shows that the resolution is thousandths of an inch. So no, it's not a super expensive micrometer, so I can live with that. So according to their markings, their resolution are the same between this caliper and this micrometer. It works a little bit different. So the caliper, remember, you had to slide it back and forth, needle move. Here, you're still measuring between the two indicators. I think I have it locked. But you turn this. Actually, there's a little clutch on the back over here. Maybe you can hear it. Like, it won't let you over tighten the whatever, clamp down too hard on what you're clamping, or well, measuring. You're not trying to clamp it. If you turn the clutch on the end, and you're reading right along here, so all the way closed. I don't know if I want to run it all the way closed or not, but let's see. We should have zeros lined up. There we go. So we're at 0 when it's all the way closed, and I might have to zoom out a little bit so that you could calibrate this by moving the plunger. I can't remember if this is called, we're going to call it the plunger. I don't know exactly what it is. Or adjusting where this guy's at, the seat on the other side. But it's better, I think, for measuring like cylindrical objects or things like that. You could obviously measure something rectangular if you wanted to, but the way it works with having a larger area here, it's actually a little bit better for measuring something cylindrical. I got to get it large enough to. Oh, well, before we measure, let's look at this, because this is different. Let's see if I can get it to focus on this. All right. So you're reading 0 to 1 inch will be the largest that this one, the scale runs out at 1 inch. So that's all it can do. And then you've got a set of tick marks below this reference line and above this reference line. And then you've got larger and smaller ones. Below it, if we look, let's set it to, well, let's do it to 0, because that'll be simpler to figure out. All right, so there's 0. And if you watch as this goes around, we get to, well, there's 20, 25, and it goes back to 0 again. That 25, well, where we're at 0 right now, that's lining up with the smaller tick mark on the bottom. And then you go around 25 again. Well, I skipped one, didn't I? There it is. And you're lined up with the top tick mark. So the bottom tick is going to be 0.25, well, 0.025, and then 0.05, and then you add 25 every time, the way this one's set up. So if we, well, let's do it the right way. Get it large enough to go around our Sharpie here that we want to measure the diameter of. All right, so we're getting close. All right, so there, you want to have a little bit of drag, but you don't want to crush the thing. So you get it to where there's a little bit of drag there, and then this one has a little lock that you can lock it to hold the thimble in place. And then we want to read this. We're at 0, because we didn't pass 1 inch, so 0 point, where's my pointer? 0 point, we made it past 4. We made it past, you can barely see it over here, but we had just passed the 0.25, so 0.425, and then 0.25 was actually over here, so there's 25, there's 30, and we're at 31, 2, 3 and a half. So we would call this measurement 0.43, 1, 2, 3 and a half. And we're estimating that half based on it landed, you know, kind of between 2 marks. It may not show up that well on, it actually landed between 2 marks. So the larger mark here is the 3 right there, and then the smaller mark between 3 and 4 would be in the thousandths place. But again, like I said before, this one says that its resolution is really only down to thousandths. I meant 10,000ths before, not thousandths. So this one is questionable whether this device is actually going to give me that resolution or not, although it is marked on the dial here. Or I think that's the thimble. I don't remember the names of all the little pieces. I just remember how they work. So they're really used when you need a little more accuracy. Maybe this particular one is no different than using a set of calipers, but typically they have a higher resolution, and it is down to 10,000ths of an inch. And this one does have markings for 10,000ths of an inch, although it itself doesn't say that it can do that. It tells you that it's going to give you thousandths of an inch. And they're good for, you know, cylindrical measurements or measurements of cylindrical objects, things like that, although they can be used for anything that'll fit between the 2 ends. And they come in much larger sizes. This one is a 1 inch, and they can come, you know, they can be 6 inches if you need them to be. At some point you have to decide, all right, I can measure that, but is that amount of resolution, is that tiny resolution, is that important to what I'm doing or not? You know, if you're doing this, all these measurements and trying to hold all these tolerances, and then you're building a part, and the way you're building it is not going to produce those level of tolerances and hold that kind of resolution, then you know, you might have been doing all of that for not really anything, and you'd been fine with a little ruler. So it does matter what you're actually doing with these measurements in the end. All right, so that's today's tool for what we'll look at for measuring. Let's go back to our thermistor. I've made a few changes here. I've actually put our switch in. So I marked on and off. All this switch is doing, it doesn't do anything except it will send a 5-volt signal over here. I've got it wired into digital pin 7. So digital pin 7 is not special. It just is the pin that I knew didn't have something else going on. Like 0 and 1 are the TX and RX lines that will probably be occupied. You know, if I'm sending code over the USB or serial information back, I don't want to put any of my other things on TX and RX. Some of these, I think 10 is maybe used for the SD card. I'd have to look that up. 13, there's a little LED on the Arduino itself that you can't see right now that is also connected to 13, so I didn't want to use that, although I guess you could, and then you would light up that LED also. So 7 was free. So 7 is not important other than it wasn't already doing something. The resistor, this is a 10K. I really did get a 10K this time, brown, black, orange. And that's just so that when I send this 5 volts, this is the 5 volts from the board, or from the, well, Arduino, that's in this case coming from the USB power. So when I send that 5 volts over, I don't send a really low resistance path. There's actually a resistor in that path, so I'm not sending a lot of current along with that 5 volts. So all that happens here is, it's not plugged in right now, but if I turn it on, pin 7 receives 5 volts or somewhere near 5 volts, And if I turn it off, pin 7 sees essentially 0 volts. And I'm using that in the code on the Arduino, the sketch side of things, to tell it when to record and when not to record. So if I flip it on, pin 7 goes high. I can track that in the code to say if pin 7 is high, start recording. And then I can turn it off, and if pin 7 is no longer high, it stops recording. So I can kind of clip, get everything set up and then only get the data that I actually want. And let's look at what I've got. I put a link to the code that I'm using, or at least the base code that I'm using, in the description of the video. But here, let's see, here is the site. This is a Sparkfun SD card shield, and on this page, they have this example code that you can just check just to see if the thing is wired up correctly. You've got all your solder joints working, and it's plugged in. All it basically does is, I think it says it'll go in and check for files on the card and that you can access the card. So that one's just for checking, basically. I use this other one down here. So I copied this code. Well, actually, there's a copy code button. I did that, actually. And then went over to Arduino, pasted it in there, and I made a few changes. So one thing I changed is I set up an integer variable called record. Let's just go through what else going here. So they've included, again, we're not Python right now, we're doing Arduino coding. They included 2 libraries, one for SPI interface. Remember, that's the serial peripheral interface. And SD is for SD card commands, like writing files to the SD and reading files from the SD card. So it included both of those. Chip select, there's different chips selects that you have to, depending on what Arduino and what SD card shield you have to change this to different numbers. 8 is the one that works for this shield. I added this to their code, so all of this other stuff they've written. I added this, just set up a variable called record. That's going to relate to my switch when I want to record data or not. In the setup, I did change this, or add this rather. There's that pin 7, and I turned it into an input so that it could look and see is pin 7 high or low. This is setting up the communication speed, and then they're waiting for the connection to occur so that you don't start doing things before the connection has actually been set up. The connection between the SD card and whatever serial communication you're using. Then it should, if you're watching the serial monitor, it should, once the connection is made, SD card's working, then it should say initializing SD card, and pin mode 10 is set to an output even if you're not using pin mode or pin 10. This has to be, the SD library up here needs this pin 10 to be an output. So even if you're not using that. There's the chip select, so that's pin 8. So pin 8 right there has to be an output. So 10 and 8 aren't free for you to do other things with if you're using the SD shield. If something went wrong, maybe you don't have a SD card in the reader, or there's some error, a bad solder joint or whatever, then you'll get this card failed, not present message if you're watching the serial monitor. Otherwise, you get card initialized. So you get this initialize an SD card, and then once it works or not, you get the other part of the message. Hopefully you get the card initialized. That's all in the setup, so that happens once. It just has to initialize the card and set up the communication so that it can see the card. And then you're in the loop. Here is a generic variable called data string. So this is where you're going to temporarily store all your data that you're going to write to the SD card. Here is where I use that variable I made up here. I set up the variable record. And here I am reading pin 7. So remember, pin 7 is the one, let's see, there we go. Pin 7 is the one that is high if I flip the switch to my on direction, and low if I switch it to off. So its reading is pin 7 high or low. If pin 7 is high, so 1 is high, I guess you probably could have done true also there, but I knew that 1 worked. So if it's high, then it's going to do all this stuff. This if statement ends way down here. So all of this depends on if the switch is on or not. So if the switch is off, then essentially nothing happens other than it keeps reading the pin state, and it set up that string variable. All right, so what happens is it reads analog 0, which is where we've got the thermistor right here. I maybe should have different colored wires, but the bottom orange wire is the tap into our circuit that has the thermistor in it. It starts building the string. So right here, these 3 lines build the string that's going to get written to the SD card. And it's milli-s, so that's the amount of time in milliseconds since the program started running. Not since I switched the switch on. I guess I could set it up that way, but it's since we started the program on the Arduino running. Then it puts a comma in there, comma space actually. Or no, maybe it's just a comma. Anyway, there's a comma, and then it puts the sensor reading, so analog read, whatever number it read, so like 512 or something like that. It puts that. So I should get a timestamp, comma, analog read value. So it builds that data string, 1 line, and then it opens the file. Now here's the file name. So this file needs to be on the SD card that's in the SD shield. A few rules with this. The name of it has to follow the 8.3 formatting, where you can't have more than 8 characters in the file name. So if you try to build this long file name that's really accurate, it's got the date and it's all kind of stuff in it, that might work in Windows, but it will not work on here because you can only have 8 characters. And there are other rules. I don't remember all of them. Maybe no special characters. I'm not sure if you can use underscores in there. So you have to be pretty generic on your file name. The extension, you could build that as 3, 8 letters, dot, and then 3 letters for your extension. So a lot of people use text file. I guess in this case, we're building a comma separated file, so you could build this as a CSV directly, and that would be okay. I don't know in this case, since it's only trying to open this file, I don't know if it will try to create a new file if it doesn't find that one. We could try that out. I think there's another SD dot something command to create a file versus just opening one. We can try changing this to some other name that's not on the SD card and see if it creates it or not. And then it writes this data string to it. Well, actually it writes it down here. It opens it for being written right here, and then it writes it here. So if the data file, if this was successful, it opened up the file. If it couldn't find the file, or you had a file name that's not valid or whatever, you get this error open in datalog.txt. And datalog.txt is kind of hard coded in here right now. So these don't have to match. You can put other things in here to open different files. This is just assuming that this is what you called the file. One thing about this is that if you run this, collect a bunch of data, and then you want to collect new data, the file name is the same, so it will just keep adding to the existing file. It won't overwrite it. It will just add it to the end of the file. So you'll get your new data appended to the end of your old data if you don't clear out this file or change the file name here or whatever. It's going to keep using the same file name. So you do have to be aware of that. So it's going to print the data string that we created up here. So the timestamp, comma, analog read value. It's going to close the file. And it also sends it to the serial monitor, so you can watch, if you're looking on your computer, you can watch what's going on the serial monitor. And then, like I said, this is the error if it doesn't actually work. So let's try to make this work. I got to plug in my Arduino. So we have power again now. Now, It already has this code on it. In fact, let's try to see if we can make a new file name here. So, new file, and see if it actually can create new files on here. I know that new file.txt is not already on the SD card. So let's see. It's uploading, done. All right, let's open up the serial monitor. Nothing should be happening yet because I'm still off on the switch. We'll turn it on. Well, I guess it does do this part. Turn it on. Actually, I think it did create the new file. So apparently, if it doesn't see the file name that you wanted, it will create that file. I didn't actually know that part. And then there you can see I'm adding heat. It's kind of covered behind your screen here. Adding heat to the thermistor. The numbers are going up. Letting it cool down some. The numbers are going down. We can turn off data collection. It immediately stops on the serial monitor. That all looks like it worked correctly. Let's go and let's unplug, turn off. You know, there's no power on. I don't have a power switch over here, so let's unplug it to turn it off. Get our SD card out. It's kind of stuck in there. You have to be pretty careful with these little cards because they are pretty brittle. I'm just gonna take one of these little guys. See, it goes this way, and read the SD card directly on the computer. There are ways we can transfer the SD card information to the computer. We're just not doing that. And sure enough, there is a new file .txt on here. That's the file name. Now it's all caps when it writes it, so it's not case sensitive. We wrote it in as lowercase, and when it showed up on the thing, it came in uppercase. So that's fine. Let's see if we can just rename this to a CSV and open it. Since it does, that's fine. Here it goes. Let's get that a little bit smaller so it's on the screen. There it is. There's our timestamp. Now again, it doesn't start at 0. It starts at the millisecond since we ran the program. So apparently we took about 7 seconds before I flipped the on switch. But we can easily fix that just by making a new column. This one, minus 6850. We can even turn it into seconds. We know these are milliseconds. So we can divide by 1,000. And then copy this all. Oh, I think I missed the page up. Copy this all the way down. Again, we're recording every like 100 milliseconds, I believe, or maybe every 200 milliseconds, because we have a 100 millisecond delay, and the analog read command itself takes 100 milliseconds. All the other commands, or maybe it's 100 microseconds actually. We have a 100 millisecond delay, so we essentially have, yeah, you can actually see the thousandths. I think it takes 100 microseconds for the analog read to process. So we could plot these two. Let's see and see if they look right. Yeah, that looks exactly like we would expect. We kind of saw this pattern the other day on the serial plotter, where there's an increase when you add temperature, but it's not an immediate step. We'll talk about this some today when we talk about dynamic measurements. This would be a dynamic measurement. It's a measurement that it changes with time. So our x-axis down here would be seconds basically. And you can see that there's a steady state beforehand that's around 500. And then I didn't let it get to a steady state up here. I let go of it, but maybe it was going to peak somewhere right here around 547 or so, something like that. I guess we could go find the peak in our data if we wanted to for real. Maybe I should have let it get entirely to a new equilibrium state that was hotter, but I didn't do that. And then I let go, and then it started cooling back down. So we can actually use this plot in a minute when we go to figure out things like time constant. This still isn't measuring temperature though, right? This is still measuring 500 to 550, so those aren't Kelvin, that's not Celsius, it's just analog read values. How about we minimize these for the time being? I don't think we need that. Close that. Again, most of that code that we just used was this code. I just added the functionality to turn on the data collection and turn it off with the switch over here. If you don't want or need that, then this code will do exactly, well, no, it won't exactly. Let's see. What it does is right here, this is what it's reading. So I did make another change. This code by default is reading 3 different analog pins. Analog pin 0, 1, 2, well, I think those 3. 0, 1, and 2. We only have pin 0, so you would get a real reading on pin 0 and then 2 just random whatever is floating around in pin 1 and pin 2. So I did change this up to just read analog pin 1 and not string 3 of them together. So I did change up this little block of code a little bit to only read analog 1 and add that little comma and add the timestamp. This one didn't have a timestamp in it. So let me show you. That block for me looks like this. That same block that I just had over here. I replaced the salmon colored block with the yellow colored block. All right. And that does not super important, but don't run this other code thinking it's going to do exactly what we just did, because I did change up what's actually getting recorded. All right. What I wanted to do was go to Thani though. Let's see if I have Thani somewhere open. There it is. All right. So we still didn't have our temperature measurements. We had analog read values. Let's actually go to our sheet of paper here. So let's get Thani out of the way. Maybe we can make that a little brighter. So what we had last time, our circuit diagram, just to remind us, we had something like this. This was our thermistor. This was a 10 kilo ohm resistor. This was our bias resistor. We were measuring basically this voltage right here. We called it analog read, I guess. That was analog read on pin 0 across this point and ground. You know, this is ground over here. So we were measuring the voltage across this guy, but it comes out as a number between 0 and 1023. The range there, 0 to 1023, has to do with the analog to digital converter on the Arduino itself. It's a 10-bit converter, so 2 to the 10th power is 1023. And so if you have a different analog converter, then you would get a different range of values. Ours goes from 0 to 1023. And 0 would represent 0 volts. We're putting 5 volts into our system. And the maximum, whatever it is, in our case it's 10,000 or 1023, would represent 5 volts. Not because of 5 volts here though, because our reference voltage on the Arduino by default is 5 volts. We could make that upper end a different reference if we wanted to. There's an easy way for it to be 3.3 volts, but we can reference any voltage that the Arduino can handle. It's just a little more complicated. The Arduino already has 3.3 volts on it, so it can use that as a reference easily. But the default is that it's going to reference 5 volts, so the maximum would be 5 volts. All right, we worked out last time that, let me get our equation back. I don't remember it offhand. It turns out the equation for the resistance here doesn't actually matter, doesn't depend on the voltage that's in this circuit. The voltage matters, but the equation to determine it doesn't actually matter. Determine the resistance doesn't matter, or is not concerned with the voltage. So this voltage, or no, not this voltage, this resistance, I'm going to call it R2 because we use R2 in another equation. But this is the thermistor. And it equals 1 minus this analog reading. So the number you actually get, the 512 or whatever it is. And it's on pin 0 for us. Divided by 1023. So that's basically going to give the ratio 1023 is the maximum it could read. Divided by that same term again, the analog read on pin 0 divided by 1023. And all of this quantity times RB, where this is RB. The bias resistor is just the 10,000. Now you could go and actually measure your bias resistor, whatever it happens to be. But we have this equation that will give us the resistance. And once we know that, we have the manufacturer's theoretical equation that says, so from the manufacturer, we have that the temperature that the thermistor experiences is equal to the beta value. The beta value for us was 3470 Kelvin. I'll leave the units off here, just put 3470. Time, or divided by the natural log of all of this stuff. So what is the resistance of resistor 2, the thermistor, over the reference or the bias resistor's resistance times E to that 3470 number again, divided by a reference temperature, and the reference temperature is related to this beta value. It comes from the manufacturer. So B equals 3470 K, and T1 is 298.15 Kelvin. Those come from the manufacturer. Basically, that's the temperature at which they determined this beta value. Oh, and these resistances, both of them are in kiloohms. Although I guess it doesn't really matter because you divide them, so it's just a ratio. But they are technically in kiloohms. All right. So this is how we're going to calculate the actual temperature according to the manufacturer. Another way we could do this is calibrate our sensor with known values of temperature, put our sensor in these known, maybe you get cups of water and you measure the temperature of the cups of water with an instrument you trust, and then you can calibrate the readings of your thermistor to those known values. You could do that. That's one way to do it. In fact, I think you have to do that for homework. Let's build a new thing in Python. Thani. All right. So what we're going to do here is a useful thing, and it's called, it's a function. It's a building your own little set of miniature program that you can use over and over again, sort of like a library, but you call it either a function or a method or something like that, so that you can use it over and over again. So I'm in Thani. We do have this, well, it's covered up. I'm pointing to it. You can't see it. We do have this E exponential and the natural log. So to do some of those things, we need to import math. So you don't have to install the math library. It should already be installed, but we do need to import it and reference it because we need to do some stuff other than just, regular mathematics stuff. We need to do the natural log, things like that. All right. So to create a function, the define command here is going to set up the function. We have to name it. Doesn't matter what you name it. So this is the, well, let's at least spell it the right way. It doesn't matter, but the thermistor theoretical expression. But you can name it whatever you want. It can just be X or Y or whatever. All right. We have to give it a bunch of arguments. All the things, all the bits of information that we want to put into the equation the function that we're building, we're going to list here as arguments. So R2, that's going to be the resistor of the resistance of the thermistor. B is a variable, but we're going to define this one by default to have a value of 3470. So we could go in, maybe we get a different thermistor and it has a different beta value. We could override this 3470, but we're going to put it in as a variable that can be written, but if you leave it blank, it's just going to default to 3470. We'll do the same thing with our resistance of the bias resistor. Actually, we're going to put this one in as ohms. Like I said, it doesn't actually matter. The equation, it's a ratio, so it doesn't matter if you have, as long as they're both the same. As long as they're both ohms or they're both kilo ohms or whatever. And again, maybe you go and find out that, well, my bias resistor was actually 9,872 ohms, and you can put that number in to override this one. But we're going to, by default, if you don't say anything different, it's going to assume that R1 is 10,000 ohms. Well, 10,000. It doesn't know anything about units. T1, that's the reference temperature that the beta value was created at. And that came from the manufacturer. That's Kelvin. Here, we're going to say that most of the time, you don't want the thing to be in Kelvin. Now, Python doesn't know that Kelvin means anything. It's just a word. It doesn't mean anything related to temperature or anything. We're going to tell it in a minute, hey, if you see this Kelvin, do this. If you don't see it, do that. So we're going to say that by default, most people want to know the reading in Celsius, not in Kelvin. We put our little colon here to say that that's the end of our naming the function and putting up all the arguments, setting up all the arguments that might be part of the function. All right. We are going to convert between Kelvin and Celsius. By default, this equation, the manufacturer's equation that we had over on the paper, it is going to give you temperature in Kelvin. So to convert between Kelvin and Celsius, you just subtract off 273.15 degrees. So if Kelvin, here is, if this is true, by default we set it to false, but if it's true, then unit conversion equals 0. That means that we're not going to subtract off 273. It's in Kelvin. We're going to leave it the way it is. But we have to override this false statement because by default we've set it up that it's going to give us the answer in Celsius. All right. Temperature equals B. So by default, B is 3470. Divided by, we need that math library to do the log. R2 divided by R1. So there's the ratio of R2 and R1. Now it does not have a value hard-coded in for R2. So that means that we will have to supply at least that. All these others it has default values for, but we have to at least supply the value for R2. So R2 over R1 times, we need to do the exponential, or the E, B divided by T1. And then we're going to subtract off this unit conversion. So by default, we're going to subtract off 273.15 to convert to Celsius. But if we want it in Kelvin, we override the Kelvin equals false argument out here, then it will subtract off 0 and it'll leave it in Kelvin. And then return T. So this block is a function we have built and it converts, or it doesn't convert, it takes the resistance value of our thermistor and will output the corresponding temperature according to the manufacturer's equation. So let's say that we had, I don't know, by default it's 10,000, right? So let's do 10,000. To use this function, we would want to go in, the name of the thing, we called it thermistor theoretical expression, and then we need to give it a value for R. Let's say that R equals I don't know, 10,000. So now when we run this, it will put this value in for the first unset value. So all of these have a value already. You might have some functions that have more than one parameter that or argument that you have to give values to. Here there's only one, so I can just put it as the only one in there. Oh, I have to save it. There we go. And it comes out that, oh, if your thermistor is reading a resistance of 10,000, then that corresponds to 25. Now, it doesn't do anything formatting wise or units or anything like that. It doesn't. We could make it more fancy, right? We could add on plus C or plus K, depending on if it's Kelvin or Celsius and all that. But 25. Let's do another one. Let's say that, well, let's say we want it in Kelvin. So we give it the same value for R, but then we switch the tag from the default Kelvin equals false to Kelvin equals true. And there you can see the 25 is from the first line, and line 11 here is the same value but in Kelvin, because we switched from Kelvin false, which didn't run through this little block of code, to Kelvin true, which did run through this block of code, redefined unit conversion to be 0, and so when it was done here, it subtracted off 0. So you can change any of these. We do have to give it some value for R, but maybe R1, our bias resistor, is not actually 10,000 ohms. I think I said 9,872. Oh, but I have to give it which one is 9,872. And so it slightly changed. Now again, no formatting at all. I've got like 10 decimal places out here, which is not realistic. But you can see it did change from 25 to 24.67. So the bias resistor being exactly 10,000 ohms does have an effect of, and we're not that far from 10,000 ohms. We're within tolerance on one of these resistors at 9872. But there is, according to the manufacturer's equation, a decent difference between 25 and 24.7. So 0.3 of a degree Celsius. Mainly, I wanted to show this so that you could get the idea of how to build a function. So the function has a couple of parts: the DEF, the define command, so that it tells Python it's going to define a function, a name for the function that's not already used, so you have to give it some unique name, and then at least one argument, so at least one thing that has to go be passed to the function for it to do some processing. You can have more, you can even predefine some of them, but you have to have at least one argument. And then some way to, crunch on the numbers that you give it. And then this return statement so that it knows what to spit back when it's called. So here I've called the function with a value of 10,000 for the first unknown variable. So it puts a 10,000 right here. All of these it has values for, so it just puts the 10,000 right here. And So all the R2s become 10,000, the Bs are 3470, and so forth. And then it returns T, which is this evaluation, and it puts that out on the screen. It puts it on the screen because I put it inside a print command. So if I didn't have it inside a print, it would just return it with no output. All right. So hopefully the little demo there will give you a few more tools for coding in Python. Let's go now to linear regression. So you've got all this data. Somewhere I had a, where do we go? Here it is. Got this data, right? And you might want to create an equation that models this data. Well, we can do that. Now, I'm going to look at linear regression. That was not a straight line. And so there are ways to modify the linear regression to create power functions and exponential functions and all that. But we're going to look at if you were trying to fit a straight line through there. The same principles apply if it's curved, but we're going to start with something straight. So let's build a little graph. So that'll be our y-axis. There's our x-axis. Doesn't matter what we're actually plotting here. This can be the thermistor data, but we collect some data points, and that's where they end up at. We want to put a straight line between here. So one way you could do it is to literally go in and kind of just try to figure out, well, where is the best line going to be? Like right there. All right, and then we draw that line. So you could do that. You would never really be able to say that that red line is the best line, but it kind of models the data. Each data point does have some gap between it and the line that you created, though. It's almost impossible, unless your data does line up in a perfectly straight line somehow, then you're always going to have some amount of difference between your data points and the line that you use to model them. If you had a line that was perfectly aligned with all of them, then you might question what's going on. That's a little bit odd that they would match perfectly. I guess if you zoom out far enough, then maybe it looks perfect. You also don't want necessarily to create some line that just kind of goes through all of them. You can find a polynomial with enough roots that it will go through every one of them. You don't really want that either. That's usually not the point. So this distance is called a residual. And our strategy is going to be to minimize the total amount of residual between the data points that you collected and the line that you use to model them. And so we want to add up all of these residuals. But you don't want to just add them directly, because here I've got a negative difference. Here I've got a positive one. Here's a negative, a positive. It might be if I just added up all these little distances, they equal 0, because half are on the bottom side and half are on the top side of my line. And so that's not actually what I want. So I square these distances. So squared all these distances, then add them up. That way I actually am quantifying the residuals and not just subtracting or canceling out half of them, or all of them even. So I end up with a set of equations that would create a line sort of like this. We're trying to do a straight line, right? So let's start with that. So we want to create a straight line for this piece of data, set of data. And we could go in and I'm going to use beta. we'll call this not I, that'll be a 1. So the epsilon here is the residual. And I could create one of these for each one, right? Well, this would be 2, sorry. Well, the slope would be the same, but it would have a different error term. This beta here, this is the y-intercept, so the line that would fit best through here would have the same y-intercept. It would have the same slope, but it's going to have, with each x and y coordinate, it's going to have a different residual. So I have 4 of these, so let's make 4. Y-intercept is the same. The slope is the same. But now we're on x4, y4, and it has its own residual. And the idea is that I want these residuals to be as small as possible. So I can, now this is going to go into some linear algebra, which most of you haven't actually studied linear algebra, so there probably will be stuff that you're just going to have to accept as, well, that must be right. So if you haven't studied linear algebra, then there'll be some parts here that maybe the words are familiar, but you don't know exactly how they work, and that's okay, because we're not going to do this part of linear regression. This is just how you get to linear regression. So I could set up this equation set to say this. Now, x here is not this x, so we do have to keep track of that. So in fact, maybe we need a new sheet of paper. If we put these kind of up there, we can work down here. So in this equation, y is a matrix that is filled with y1 through 4. So that's okay. That's pretty straightforward. You can see that easily. Beta is a matrix also, but it has to have this value, and this should be a 1. And it goes down to however many you have. And then the epsilon matrix is all the errors, or the residuals. But the x here, this one's a little bit different, and it's okay if this kind of doesn't make sense right away. But what we would have here is, now really for us, there's just a beta 0 and a beta 1, right? We only have beta 0 and beta 1. But when I multiply x times beta, I would have, basically I would create all the 1s here, would create this y-intercept set, and the x1, x2 would be x1 times beta 1, x2 times beta 1, x3 times beta 1, x4 times beta 1. So these matrices combine in this way to recreate this set of equations, which are basically, there is a line somewhere that has a y-intercept and a slope, and it has, it'll go out here and kind of model all these data points, and each one has some amount of error or residual distance between the data I collected and the line that I'm using to model the data. So now I'm at this stage. All right. Yeah, we can't use that side. So let's go back to that stage. I'm trying to write these different so that they look like the matrix and not x and y coordinates. At this point, what I want to do is I want this to be as small as possible. So I don't want there to be, in my ideal world, where'd my plot go? In my ideal world, there's no distance between the points that I measured and the line that models them. But in the real world, there's some amount. But I want it to be as little as possible, so I make an approximation. And I say that, well, this is more or less this equation that I want to create, the y equals mx plus b for this perfect line. It's going to be this. And I'm just going to set that to 0. Say that there's no error. I know there is some error, but I'm going to say ideally there's no error. So that's why it becomes an approximation, because I'm saying one thing, but I know it's not quite true. So it's approximation. Now at this point, this is where you have to know a little bit about the linear algebra process for you to get to the next step. And what happens here is you can't just say that you can't just solve for beta by dividing by x, because it's not like regular algebra that you already know. These are matrices, right? They're all these matrices, so we have to follow some rules. What we have to do is multiply both sides by xt. So that's the transpose of this X matrix. I need to do that because this X matrix right here is not a square matrix. And the way I've drawn it, in fact, it's I've got 2 columns and 4 rows, so it's not square. It's not 4 by 4 or 2 by 2 or whatever. It's not a square matrix. So I'm going to multiply both sides of my approximation symbol here by the transpose of X. Now, this, when I multiply a matrix by its transpose, if it wasn't square before, it is now. This term is a square matrix. X multiplied by the transpose of X is a square matrix. Now I can do something useful, and that is I can invert this matrix and multiply both sides by that. So I'm going to multiply. I've got all these x's. Some are multiplied, some are the matrix x. So I'm going to do this. I'm going to take this set, invert it, and multiply both sides by that. So what I get now is xt inverted times x transpose y. So that's on the left side. And the other side becomes this, xt times x transpose inverted. And this is special. So I took a square matrix and multiplied it times its own inverse. What I create there is called the identity matrix. So I is the identity matrix. And that's like multiplying by 1 in regular algebra. So now I have beta equals, because this identity matrix, it's a special matrix that basically has the ones along the diagonal. It's a square matrix. Ones are along the diagonal and zeros everywhere else. So basically, if you multiply something by the identity matrix, then it is the same thing it started as. So now I've got beta equals this. And that is how I can solve for the beta, which way back over here was going to contain beta naught was the y-intercept, beta 1. In our case, we only have one slope, so beta 1 is the slope of the line. So we'll get y-intercept and slope from this. So all of that, just so you have a little better idea of how this actually happens. There's another way that you can go through this. In fact, I think you probably did, is in a freshman class maybe, that has some summations everywhere, and it didn't do the matrices version. This is what linear regression, when you're using linear algebra to do it, this is what it looks like. This now that we have matrices, all these matrices are the y coordinates, the x coordinates, a bunch of ones, right? We set all these to 0, and so if we have all the all the x coordinates, all the y coordinates, and we're able to put ones somewhere, then we can solve for our slope and well, I pointed the wrong one, the intercept and the slope, using this. So we could build another Python function, for instance, that takes the x and y coordinates and runs through this matrix math and spits out the y-intercept and slope of the linear line, y equals mx plus b, that will best model our set of data that we have collected. I know that you could do the same thing by going into Excel, plotting. You know, we could go to Excel, and if we chop off the data that we don't want, then there's a add trend line, right? So linear trend line right there. This is the same thing, only done in Excel, that we're doing here. And you know, you can make different, well, so can't do some of them because of we have some 0 values in there, I guess, somewhere that make it not want to do logarithmic. Could do a polynomial and change the order to get as close as we wanted to, you know, but at some, well, actually, I guess I'm maxed at 6 on Excel. So that's what's happening when you right click, add trend line, linear. This process with the matrices is behind the scenes doing that sort of thing. All right. On Moodle, there is a Python function that will do this. That will do this part. It shows you how to write this into Python. All right. Let's see. Let's do. I think we're almost done for today. Yeah, let's look at this guy. Look at this. Let's get rid of that trend line. It's kind of silly. I don't know how to get rid of it now. Oh well, it won't bother us. I wonder if I can just delete it. Sure can. All right, so we got this. This is dynamic data. One thing that when you have a dynamic system like this, you know, it could be a first order system, second order system, whatever. Is that they have a time constant. And this time constant gives you an idea of how long it takes to reach from one equilibrium state to another equilibrium state, right? So we have an equilibrium state down here, and then we kind of maybe have an equilibrium state up at the top. It's hard to tell. I should have probably kept the heat applied longer to see if it actually leveled out there or not. I guess I got tired of waiting. Anyway, it looks like it was going to reach equilibrium. It's kind of topping out right there, it looked like. So this time constant idea talks about that. Now we have to look at, and we don't have to solve any of this, but we have to look at some solutions to first order systems. So looking at this graph, get that in your mind, and we'll come back. Actually, I'll just draw a picture over here. So thinking of that graph that came from, basically all I did was I held the thermistor for 10 seconds, it looks like, and then let go of it, right? We're going to ignore the let go of it part, because that, you can even see that heating is one thing, and then cooling looks different, right? It looks like it's taking a much longer time for it to cool. So there is some difference in heating. We're only going to look at the heating side. So here's a little mini picture of our graph. Let's draw it some other color. Let's see. So it had some steady state before we started. And then if we had kept holding it, it would reach the new steady state. All right. So the solution to a first order, we're assuming this is a first order system. It looks like a first order system, and it behaves like a first order system. If we actually did the heat transfer equation for temperature, it would look something like Q is equal to the mass of this little, oh, it's off the screen, this little guy, times its heat transfer coefficient, times the delta T, so from what temperature to what other temperature, over how long it took to get there, so dt, the change in temperature with respect to time. And that's a first order system. We don't see any second order terms in there, so it's a first order system. And first order systems tend to have this kind of response. So a solution to a first order system is, so x of t, so that's the t is time here, not temperature, over x naught, so that's the initial starting point that we're going to go with, this is the SS is steady state and initial, so all the naught is the initial, in this case temperature, this is the steady state temperature, equals E negative T over tau. So T is time, X in this case is actually the temperature, tau is the time constant. And so that's the thing that a lot of times we're interested in. We want to know what the time constant is. It tells us things like how often we can reliably take a measurement if we're changing things. You know, if we're expecting it to have reached the new equilibrium point or whatever, it gives us some information about the system and how to describe the system. It'll also let us model the system if we can calculate the time constant. It'll help us create this equation, or create the first order equation that goes with it. This guy. So let's take our numbers. Well, now our numbers again are not temperature numbers. We never converted this particular data set over to temperature. They're just analog read values. So they're actually related to the resistance. To the directly related to the voltage in the bias resistor. So they're not even, measuring the resistance of the thermistor, the numbers that we have on our plot here. All right, so let's see. It looks like pretty much for us, x naught, this number down here, that's pretty much 500. And then this number, the steady state, is let me see if I can find it. It looks like it's going to be somewhere around the 18-second mark. Here, you can watch me scroll. Somewhere in here, there's a 548. Looks like it maxes out at 548. All right, so we'll go with 548. I don't know if we need to be that exact or not, but that's what we'll do. So 548 and 500 for our initial condition. So what we can do here is that if we know that we want to find the time constant, let's just take the special case of this equation where the time constant equals tau. So special case t, the time, equals tau, the time constant. So what that does is it puts a tau in here, right? So x of tau minus the steady state number for us is 548 over the initial number is 500. Steady state number again is 548 equals e to the negative t, which is tau, over tau. So that's e to the negative 1, which we can actually evaluate. E to the negative 1 is 3679. I guess you have to approximate that because you are rounding, you know, goes on. Now I have an equation with only one unknown in there. The only unknown is x of tau, and I can solve for it. So therefore, x of tau equals, I'll have to get my calculator because I don't know, I didn't do it beforehand. We just collected this data. So 0.3679 times 500 but minus 548. And then we need to add 548. 530. 530.3. All right. So what I do with that is, let's do it on here. So remember that number, it's 530. So 530 is this point right here, right? Let's add some more decimals, or not decimals, but timestamps down here. Okay. So 530, I look and I'm right past 11 seconds. But I didn't start at 11. I started at 9.5. So I started heating at 9.5, and it takes it to 11. Let's say 11.25. So let's go back over here. So this point is 9.5 seconds, and this point is 11.25 seconds. This is the 530 number we just calculated. So tau is how long it takes to get from the steady state to this value of 530. So tau would be 11.25 minus 9.5, 1.75 seconds. So we would say that this system, whatever we have set up here, has a time constant of 1.75 seconds, so around 2 seconds. Another way to think of it is that it takes about 2 seconds for the system to reach its new equilibrium point. In this case, to reach 63%, I guess. Of, you know, if this is 37%, more or less. Basically, if you look at this, it's just saying this ratio is 37%. So it takes about 2 seconds to get to 63% of the final value that it's going to get to. And we can use that later on. Hey, I think we're back. All right, yay! I am back. All right. Let's see. What were we even talking about? I'll have to chop that in the editing thing, I guess, so we don't have to sit there and wait to see if I come back or not. All right, I think the internet just kind of hung up on me. All right, I was talking about this time constant idea. I don't really know exactly where it cut off on your end. All right, good. So you can hear me, you can see what I've got. I think, let's just start back with the idea here, and I don't know exactly where it cut off at. So the idea is that we have the solution to a generic solution here to a first order system. We know that our temperature response from the thermistor should be a first order system in this kind of form here, just from the theoretical expression for heat transfer. And we took our actual data, so this represents our data. I have it over in Excel, and we have our steady state value. Now, we did not convert to actual temperature readings. We left them as the analog read values, but they represent temperature. So we could convert these over to temperature. We actually did some of that earlier today, I guess, in Python. So we could get these, but they represent temperature. We took these actual data points and plugged them into the solution to a first order system. And we took the special case where time and tau are the same value. So basically we set t equal to tau. We don't know what tau is at this point, but we set them equal to each other so that we have x of tau minus the steady state value. Now, it might be confusing at first. You're looking at x, 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 and you're thinking along the x-axis. These are, maybe this would look better if they were y, because we're actually reading the y values. So we have x of tau minus the steady state value for us was 548. So we have 548 divided by the initial value for us was 500. So 500 minus the steady state that we reached when we finished heating was also 548. And then when you take tau over tau, and actually negative tau over tau, that becomes -1. E to the -1 is approximately 0.3679. All right, so we have an equation now that we can solve for the time constant tau. Well, actually, we don't solve for the time constant. We solve for the temperature reading, or in this case, the analog read value reading at tau. So we got that at tau, x, or the analog read value, should be 530. We went to 530 on our graph, and then we read down on our time axis, and it said that that represented 11.25 seconds. That was over in Excel. So if we knew that we started this heating at 9.5 seconds, and at 11.25 seconds we reached this point here where t is equal to tau, then that amount of time from 9.5 to 11.25, that is the time constant. And that's where we got our 1.75 seconds being the time constant. I think the only other things, we were practically done. So the only other thing, there's one other thing I guess I wanted to show you now that we're actually back. And that is that there is another way that we could also approach this same idea. And that would be to use the differential equation from a first order system given a step input. So a step input, let's make sure we all define these things the same. So this would be a step input. You have nothing, and then immediately you step up to some new value, some new input. So that is like the thermistor is sitting here out in the air. That's reading, it's reading a number, and then it immediately gets a change. So that's the change. Me adding heat to it is the step input, and the thermistor can't respond that fast, so it responds. It's going along, and as soon as it encounters the step input, it begins to respond, but it takes it some amount of time, right? So it can't respond immediately to this step input. And some systems can respond faster than others, and all that kind of stuff, and that has to do with the time constant. So the general differential equation for this is, there's our time constant again. This is the first derivative. This guy is the heavy side function. That is the step input. So the step function is that guy. Actually, not quite. This is a unit step input, so it's 0 to 1. So you have to multiply it times this value to see, to scale it, basically, to make it match this one. All right. So if I know this, then at t equals 0. Now I'm t equals 0 is this point, right? It's not all the time before where we're just sitting at equilibrium. We're assuming t equals 0 is the instant you apply the change or whatever. So same thing happened over here where the time constant isn't 11.25. It's the difference between 11.25 and where we initiated the change. So the t equals 0 here is at the beginning of the step input. So if I put t equals 0 in here, I get tau times x, the first order derivative at 0, plus x at 0 equals, and this stays the same, steady state. I didn't need those extra parentheses, but I put them in there, I guess. This becomes just 1. So it gets a little bit simpler. First order derivative at 0. X at 0 is x naught, so the initial value. And again, these x's are really y values on my chart. So don't get confused with that. So this is really the 500 here, and this is really the, what did we have, 548? So that's x naught, and that's steady state. It's not the, because remember t is along the, what we would normally call the x-axis. All right, so the only new thing here is this guy, the first order derivative at time equals 0. So that is the slope of the line, and maybe I should put initial slope at t equals 0. So it would be this guy. If we came in here and we were able to determine this initial slope, that guy would be, the slope of that would be, or the slope of that line would be what's going to go in here. We could obviously rearrange this equation to solve for tau. The steady state value minus the initial value, those are pretty straightforward, divided by that initial slope. So there might be some difficulty in calculating that slope. So what we would have to do is you either have to have all the little data points down here so that you can calculate a rise over run type thing. We do have that in Excel. I guess I could go pull them out of Excel and figure it out. But you need to estimate or calculate the slope of this line so that you can plug it into this equation. Basically, you're gonna have to approximate it or whatever, but rise over run. So if we had this point and this point, then we could approximate that slope and then just take our steady state minus our initial value and divide by that slope, and that's another way to calculate the time constant. Depending on what you actually have to work with, it might be more of a graphical way, because maybe you have to graphically estimate this slope. If you have all the data points, then you could go and actually do some finite difference type approach to find the slope here mathematically. If you have those beginning data points, you could figure it out. Maybe take the first couple of data points here and fit a straight line through them, and that'll give you that initial slope. So that's another way that you can get time constant. two different approaches. One where you use the definition of e to the negative 1, and another where you need to figure out the initial slope of your, how fast did it take off. Obviously, the faster it takes off, the shorter the time constant is going to be, the smaller the time constant is going to be. I actually think that's all we had left to do. We talked about our calipers. Yeah, we talked about our calipers. I walked through, I don't know if you need more detail. There is, on Moodle, there's more detail about getting this switch soldered up. There's nothing really tricky about it. Maybe I should show you what's inside the switch, just so you know what's going on inside there. This is just a little two-way switch. If I can get the page to turn, I will draw it. So the little switch there is basically a box. And there are 3 legs coming off the bottom of the box. So these 3 legs will go into the little prototyping board over here, and you can solder them to the other side. But what's inside the box is you've got the switch, right? And it can go to one of 2 positions. So let's say it's over here. And on the bottom of it, and I don't know what it exactly looks like, but there's something conductive on the bottom. And so when it's in this position, these 2 pins are connected to each other. And then when you slide it over to the other, these 2 pins are connected to each other. So the middle pin is either connected to the top or bottom. So in our setup, I have it so that when it's in the bottom, that's the off position. So I actually don't have anything connected here. So it's just going through the board and it's not doing anything. So basically there's no power running through it. When I switch it to on, switch it up, that's what I've drawn here. And I've got 5 volts going in here. And this pin is connected to pin 7, and actually the 10 kilo ohm resistor is also on that pin. So that when I slide it here, I'm connecting 5 volts to these 2 things. And when I slide it over here, I'm connecting these 2 things to air. Nothing there. I'm not grounding them or anything. It's just nothing is there. So that's what, maybe that'll help when you go to build this switch, to know why there's 3 pins and you don't use one of them and that kind of thing. Okay. I think that should get us everything that we need for today. It would have been a little bit shorter had we not had our little break, but maybe that is okay. Maybe we can start scheduling breaks. I don't know. Maybe you need a break. I will see you guys on Tuesday. I don't know of any announcements between now and then. If you have any questions, let me know, and I will do my best to answer them. All right, we'll see you. I'll go edit the video for that little block in there to maybe chop out the time where it's just dead. I don't actually know what it recorded, if there's anything there. But hopefully I'll clean it up for the people that watch it later. All right, see you on Tuesday.